Today, we will talk about how to compare two systems. And so first thing we talk about is sample versus population. It turns out we have already discussed that previously, so that might be a repeat. But then we really want to get on to confidence interval and then comparing systems by confidence interval visually using confidence intervals. And so the rest of it is all about different confidence intervals, and then sample size for determining means and proportion. That says that how big samples do you need, okay? And that applies to measurement as well as simulations. So sample is came from the French, as I said before. A sample, it means example, and that means an example is not a definite statement. All right, that means it is a best guess. That means there is a probability of being right and probability of being wrong based upon that example, right? And so that's what we are going to talk about. What is the probability of being right and what is the probability of being wrong? So if you generate several million random numbers with mean mu and a standard deviation sigma, and from those millions you take n observations, let's say 100 observations, the sample mean will not be equal to mu, guaranteed almost. There is some chance that it might be equal to mu, but the sample mean of 100 observations, even though you generated it correctly from a distribution whose mean was mu, but the sample mean will not be equal to mu. So sample mean is not the same as population mean, and population mean is unknown. In most of the situations, we don't know what the population mean is, and so we use the letter Greek letters for that. As I said before, Greek is kind of difficult, right, as compared to English, which we use for the sample. So the sample is easy to get, and we use English letters for those. So if you take k samples, so you have million numbers and you took one sample of 100. Now starting one sample, you take 2 samples, 3 samples, 4 samples. As you increase more and more samples, you will get more and more sample means. And so now what you can do is, based upon these, you somehow want to put some bounds of probability being wrong or right. So we put 2 bounds, C1 and C2, and we say, well, based upon whatever I know so far, the probability of being wrong is 5%, but 95% chance is that I am, the population mean is in this area, in this range. Okay? So that is what is called confidence interval. Basically, the probability of being wrong is alpha, that is called the significance level, and generally that is either 0.05, which means 5%, or 0.1, which means 10%. R could be 0.0001, means you want to be really 99.999% sure, which is often we use. For example, when we design our networks, the probability of a data getting wrong to you is 10⁻⁶. That means actually it is 6/9 is very common. So 10⁻⁷. And that is actually not the probability of data being wrong. That is the probability of data. It could be as much as 10⁻12 in some cases, in some situations, in some applications. So we are, that probability of being wrong could be any extreme small value. Okay? But as I said before, we might use just 5% or 10% as a common value. And so when you say 5%, you want to be, when you say 10%, you want to be 5% wrong on this side and 5% wrong on that side, and you want 90% to be this area. All right? So when we say 10% error, then significance level is 0.1. Alpha is 0.1. Your confidence level is just 1 minus that. So confidence level is 90.9 times 100, generally we say in percentile. So we say 90% confident. That means probability of my being correct is 0.9. Okay? And so basically, all we want to do is we want to get two bounds, C1 and C2, such that given whatever we know so far, we are sure that the mu lies in that range. Okay? Now, so how do you get it? So we'll present a formula here and then we'll show you what the formula is based upon. So let's say you want to get 90% confidence interval. Then you want to have 5% error on this side, 5% error on that side, and we know that the means are normally distributed. Why are the means normally distributed? Anybody remembers the theorem? Central limit theorem. Central limit theorem says that regardless of what the original observations are distributed with, when you take many of them and you add them together, the means are normally distributed. So the sample mean is normally distributed, and therefore if you take a lot of sample means, they will have this distribution. Okay? And so we want to find out this 0.05 point and the 0.95 points, which you can go into the table. And so you go to the table and find what we call Z 1 minus alpha by 2. Z means unit normal. Unit normal means 0 mean and 1 standard deviation of 1. So we go to the table and Z sub 1 minus alpha by 2. Why 1 minus alpha by 2? Because if alpha is 0.1, then alpha by 2 is 0.05, and 1 minus 0.05 is 0.95. And so we find out that, and since it is basically a normal distribution, it is symmetrical around the 0, standard normal. So whatever is on this side, the same value minus same value happens on the other side. So this is minus Z sub 1 minus alpha by 2, and this is plus Z sub 1 minus alpha by 2. These two values are basically plus and minus, right? So we take whatever we measured, x bar minus Z multiplied by s upon square root of n, and comma x bar plus Z multiplied by s upon square root of n, and that gives me some range with which we can be confident that 90% chance that the actual mean, the population mean, is in this range. Now, there are a few multipliers here, let's understand those too. So one thing we understood is that the sample mean is normally distributed because central limit theorem told us so. However, there are two more things. One is that since this sample came from that distribution, it really is normally distributed with mean of mu. All right? And therefore, so that is one thing we know. Second thing is we found the standard deviation, and if the sample standard deviation is then basically sigma upon square root of n. So why is that? So sigma is the standard deviation of the original population. If you take one observation, two observations, you will find that their standard deviation is sigma, right? However, when you add those things together, the variance goes down, right? And as you add more and more and more, you will not, actually this is a simple thing about adding normal variables. If they were all normal, you can very easily show that if you had one normal distributed samples or observations, you take one observation, it will have a standard deviation of sigma. You take two observations, you add them up, their variance will be equal to 2 sigma, their variance will be equal to sigma square by 2, and so its standard deviation would be sigma divided by square root of 2. When you take 3, square root of 3, and so on and so forth. So when you take n, the mean will, so basically the sample mean has the mean of mu and the standard deviation of sigma upon square root of n. As n goes up, this standard deviation goes down. What that means is that this width of this graph, width of this curve goes down and down and goes thinner, and the curve becomes thinner and thinner, more peakier and peakier and peakier. If you take infinite observation, then you can be very sure that the sample mean is same as the population mean. Okay, is this point clear? That is the advantage of taking many more samples, because as you take the samples, more and more samples, your variance goes down, your variability goes down of the sample mean itself, and then you can be more and more sure about the population mean. And so basically mu we don't know, but we know that x bar is 90% chance that it is between this value mu minus this and mu plus that, and therefore we think that the mu is in this range. So here's an example. Let's say x bar of 32 observations, x bar is 3.90 and s is 0.95, which is the sample standard deviation. So we put that 3.90 minus plus s upon square root of n, and this is the z value. How did this come about? We go to the book and we have to read, and please open the book if you have, to the table. You read it on table A2. On table A2.95, you read under the row which says 0.95 and the column which says 0000. Everybody found the page 629? Yeah? So there in that column and that row it says 1.645. And why we read the first column? Because we want 0.950. The first column is for 0. If you want 0.951, you read the second column. 0.95 to third column, and so on and so forth. So 1.645 is the z value for a normal unit normal distribution, so that it reaches 0.95 at that value. And since we want 90% confidence interval, we are reading the 0.95, 95. Why 95? Because you're not only that, because you want 5% error on this side and we want 5% on the other side. Even though total error is 10%, so we want 90% confidence interval, but we read 0.95. Right? 1.645. Now, those of us who do this all the time, we remember this number 1.645 because it is such a common thing. And however, in the real world, what will happen is you will not always be doing 90%. You might be doing some other confidence interval. And so you will have to read, get a table and things like that, right? And so anyway, so with that 1.645, if you put that number, then we get the range 3.62 to 4.17. So that is the range. So basically based upon these 32 observations, all we can say is that the real population mean is in this range, and we could still be 10% wrong. And suppose you want a 95% confidence interval, not 90%. Right? So then you have to read the table. Can you read the table now and find out what number to use on the table? For 95%, what are we reading first of all? 0.975. So 0.975, how do you read 0.975? What row and what column? So the row is 0.97 and the column is 6th column. Right? And there it says 1.960. Now, first thing you should notice is that which one is wider, the 95% or 90%? Yeah. So basically, I am sure 90% sure that this is the range, but if you want to be 95% sure, then this is the range. If you want to be 99% sure, then this is the range. The more surety you want, more confused I am, basically, in terms of I have to bigger width I have to give you. You understand? If I wanted to be just 10% sure, then basically it would be I can be very sure that it is close to 3.90, maybe plus minus a little bit. All right. So as we increase the confidence level, the interval increases. All right, so 99% confidence. Similarly, for 99% confidence interval, what do we read on the table? Anybody else? Yeah, 995. So let's see, how do we read that value? So we go to the table and read 995. So we go to the 995, actually it turns out to be the first column of that row, which is 995. Okay, everybody sees that? It is in the first column, not the 6th column or anything. It's in the first column, 995. All right, so we put that, and now it comes out even wider. It was something like it was so, now it is even wider than that. So 99% confidence interval is even wider than 99 and 95, and that is wider than 90, and so on. So do you feel comfortable that you can get the confidence interval? Everybody? Okay. So the meaning is that whatever interval I specify, I would be right 90% of the time and wrong 10% of the time. If I take one sample, based upon that sample, I will come up with a confidence interval which goes this wide. Right? And we will say that the mean is in this range. If I take another sample, obviously my confidence interval will be totally different. So with this other sample, I will say that I expect that the real mean, population mean, is in this range. With the third sample, could be different, 4th sample, 5th sample. If you do it 100 times, you would be wrong some of the times, like this. But you'd be right how many times? 90% of the time, or whatever you are talking about here. So when you say confidence interval, you are 90% sure, so you could still be wrong 10% of the time. Okay, makes sense? All right, so for small samples. Now, here is the thing. Basically, the way all this confidence interval thing worked is because we assumed that we have a large number of observations. That means we have a large sample, and therefore the mean is normally distributed. If we don't have a large, and by the way, large sample is defined as 30. Okay, that's not absolute boundary. If you have 29, it won't be normal, and 31, it will be normal. No, that is just for most of the time. That is how it works out. There could be exceptions where the distribution is so weird that with 30 observations it is nowhere close to normal. It can happen. Okay, but without any further considerations, if you didn't have any more data, then you will say, well, 30 observations will make it generally normal, and so it will apply to any distribution. All right. However, if you don't have 30 observations, then what do you do? One thing you could do is you will say, well, I really don't know then, because obviously the mean is not normally distributed. But if you make one more assumption, then it becomes solvable problem. The second assumption you make is that if we assume that the observations themselves are normally distributed, then the problem becomes simple, because then, you know, the 2 and 3 and so on and so forth remain normal. So the mean would be normally distributed, but the standard deviation part, which we didn't discuss before, and I would right now not go into detail, is that then the sums of the normals are normal, but the sums of the squares of the normals have a distribution called chi-square, and based upon that, you know, if you go into the ratios and all that, you will come out that really the standard deviation multiplier, this thing where we had z, will now have a t distribution. And this will become clear actually by the time we reach chapter 29. So those of you who are interested could go to chapter 29 and read it there. But right now it is too advanced for me to, you know, jump to that place. Let me see chapter 29. And chapter 29. Okay. So in chapter 1, page 497, there is something called students' t distribution. So that is where it describes what t distribution is all about, and it shows that t distribution is the ratio of normal to square root of chi-square and so on and so forth. And so based upon all that observation, you can say that basically, since this is what is S, if your observations are normally distributed, then the way you calculate sample variance is you square the observations and then you add them up. So the sum of the squares of the normal is chi-squared. Then you take a square root, and so things like that. So basically, when you do that, it turns out that this is the formula, t distribution. So the key thing to notice at this point is that not only that you cannot use z, use t. The second thing to notice is that this makes two assumptions. One, that you have the additional assumption you are making now is that the observations themselves are normally distributed, which was not the assumptions we had made before. Clear? So if with that assumption we can do it for small samples. However, this t distribution has two parameters. For different values of n, the t value is different. So the second parameter is you have to read at n minus 1 what we call degrees of freedom. You have to read that, and the confidence interval is 1, and what we call significance is alpha by 2, and the confidence is 1 minus alpha by 2. So now you have to read in the table, and you might as well leave that page open because we are going to go there so often. So we are going to read the table which is t distribution, which is on page 631, table A.4. In table A.4, when you read it, it has two rows. One is the probability, second is the degree of freedom, and the table goes, you know, for n equal to different values. All right. Okay. So once you realize that instead of z you have to use t, then you get the confidence interval as before. So here is an example. this is a small sample, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 maybe, right? 7, 8 observations, 3, 8 observations. So the sample mean is 0, sample standard deviation is 0.138, and so for the 90% confidence interval we have to read 0.95 and n minus 1 is 7. So 0.95 and 7. So we go to that table and then we read the 7th row. You see, even though there are 8 observations, it says n, but really there, here in the table n means the degrees of freedom, which actually is 7. Okay, so don't confuse that n with the number of observations. When you're doing here, the number of observation is 8, but when you're reading here, it is n minus 1. You have to read degrees of freedom. So and I don't know if anybody remembers why n minus 1 degrees of freedom are left, and when you do standard deviation. Anybody remembers why n minus 1 degrees of freedom are left? Yeah.
I believe it's because you take the mean of the population.
Yes, you are taking the sample mean. If you calculated the standard deviation using sample mean, then you use n minus 1. If you calculated the standard deviation using population mean, which you by some chance you might know, then you use n, right? But so that is the reason. So the same reason. So basically, so here we have n minus 1 degrees of freedom, 7 degrees of freedom, and we want confidence of 0.95 for 90%, and therefore we read 0.95 and 7. So if we go there, that is the 7th row and the column number 1, 2, 3, 4, 5th column. And then the 5th column, it says 1.895. Is that the number? Yeah, 1.895. So we use 1.895, and my page changed. How come? Okay, 1.895. So 0 plus minus, minus plus 1.895 times s. Oh, that's another thing, is that we don't have a square root of n here. S upon a square root of n. S upon a square root of n. So that's the typo. Okay. Yeah. So it's typo only in the slide, not in the book. In the book we have it correct. Okay, can I have a handout? In the book it shows you a square root of can I have pen also? A square root of 8 over there. So square root of n on the slide. Okay, so basically I need to put here 0.138 divided by square root of 8. And so here also 0.262 divided by square root of 8. So all of these numbers will change. I don't understand how the book is correct and the slides are wrong. Yeah, the book is correct. Okay, everybody got the right answer? All right. So some of you already know confidence intervals and you know this part, but what is less commonly known and is more important is to visually check things out. So whenever you plot the confidence intervals, generally what you do, you put a dot at the sample mean and you just draw a line which width is equal to the confidence values, right? Now we can do several things with this though. If the zero line crosses the confidence interval, that means that the population mean could be 0. Right? If the zero line does not cross the confidence interval, then you could be very sure that the population mean is non-zero. Right? And similarly here, in these two cases, you could be 90% sure, or whatever number you used for the confidence, you can be sure that the population mean is non-zero. Here you are kind of not sure, and so you could say, well, given the data that I have, based upon that, it could as well be 0. Right? And this is a very powerful observation. Why? Because now you can distinguish a 0 from non-zero, in the sense that you can distinguish whether this number is really has any what we call significance or importance, or or things like that. Okay, so let's see. So we measure two processors, and the difference in the processor time comes out this. This is the difference. So we basically take the mean. The mean is 1.03, and so most people will make a big deal about this 1.03 and say, look, this processor is better than the other. Right? But if you do it right ways, then what you will do is you'll say sample size is 7, and I don't know whether you need the pen, but 7, sample size is 7, and therefore we can use the T formula, 1.03 minus plus T. Now we need to read at 6 degrees of freedom, and let's say we want to read 99 percentile. This is 99. This one is 99% confidence, right? So we read 0.995 value from the table, and that value comes out to be 1. Where is the value? Is 3.707. Okay, so we multiply 1.03 minus plus 3.707 star 1.6, which is the standard deviation, divided by square root of n. And if you do that, you get the 99% confidence interval is minus 1.21 to 3.27. Okay. Now, given this data, what will you say about the difference in the two processors? Huh? There is no difference, because there could be 0. The difference could be 0, because this interval includes 0. So now, the important thing is that whenever you see a confidence interval, you look at these numbers, and without doing too much mathematics, too much statistics, too much probability theory or hypothesis testing or whatever, you can see the numbers right there, and minus and plus means that includes a 0, means as good as 0. Okay. If you were to do a very strict hypothetical test, many of the books have a hypothesis testing section, statistical books. And so what will happen is, with 99%, you do the hypothesis testing, the hypothesis will fail, in the sense that the difference is 0. Basically, that's the same answer you can get without doing any of those statistic things, just looking at the two numbers and seeing if the signs are different. If the signs are different, then regardless of what those numbers are, it includes a 0, and therefore the difference is 0, as good as 0 actually, and at that confidence level. Now what can you do? So we did 99%, and now it includes a 0 here. What I have to do? I have to say, well, at 99%, I think this difference is not there. But if you want to be error of 10%, the confidence interval narrows down. At some point, the 0 will be out. Right? When the 0 is out, then you can say, well, if you want 80%, then yeah, the difference is, maybe non-zero. But, I could be wrong 20% in that case. So, opposite signs means that we cannot say with 99% confidence that the difference is significantly different from 0, and therefore they are the same, and that the difference is 0. Okay, either one you can say at that confidence level. So now you are making probabilistic statements, and so like that. Okay, so now here you think. I don't know whether this is a different example, but we take these numbers, and the question is now we are extending another thing. So why 0? Suppose the question is not about 0, the question is about 1. Is the difference 1 between the two processors? Now look at the confidence interval. Since 0 was included, we said, well, it could be 0. Right? Now 1 is included too. So the difference could be 1 as well. Right? So the answer is yes. The difference could be 1 as long as you are 99%. Okay, I could be wrong at 9.1% of the time, but So the thing is, in this range, we can't say much. We cannot differentiate anything. Outside this range, we are sure that that the error is only 0.1%. Sorry, the error is only 1%. So the confidence interval, anything in this range could be possible. The sample mean could be 1, it could be 0, it could be -1, it could be +3. Right? That's all we are saying. We are saying that this population mean is somewhere between -1.21 to 3.27. All right. So here is the homework. For the exercise 12.11, regardless of what the data is, you have to find the 10 percentile and the 90 percentile from the sample. So this is not the confidence interval. This is just calculating the percentiles. Sort the numbers and calculate the percentile. Right? Then you get the sample mean, sample standard deviation, and you get the confidence interval. So they are different. Percentiles are different than the confidence interval. And then the question is, what fraction of programs make less than or equal to 25 IOs? What fractions of programs? This you can just read from the data. You can just calculate how many programs made less than 25 IOs, and that will give you the percentage right there. And what is the 95% confidence interval for the fraction? Now this is something that we have not done. So this homework you cannot do until we go to the fraction. So just hold on to that one. This one, if we don't get to that fraction thing, then this will not be due. Now what is the one-sided for the mean? Okay, so these two things actually, one-sided we are going to do just in the next few slides, and the fractions a few slides after that. Maybe I should move the homework after those two things, but right now these three things you can do. All right, so I think one-sided is coming here. So that exercise is little bit too early. All right. So let's talk about using the confidence interval for comparing systems. So we already saw few examples where we compared two systems and we said, well, they are really identical, even though the sample mean is 1 point something, but that confidence interval includes 0. So we are going to use that kind of thing to compare systems. But before we really use it, we have to understand a difference between what we are talking about. So there are two kinds of observations: paired observations and unpaired observation. Paired observations means we have one system on which we did something, and we have the second system on which we did exactly the same thing again. So the first number here corresponds to the first number here. Workload benchmark 1, benchmark A, or spec benchmark on the two systems. Then we took some other benchmark and we did it on the second system, right? So these two numbers are related. Then we took the third benchmark and we did it in both systems, third number. This is called paired observation. Why? Because each observation on this side has a relationship to the corresponding observations on the other side, right? On the other hand, you have unpaired observations where you just ask 5 random people from one state and 5 random people from some other state. There is no relationship between the first person here and the first person there, right? So those are 5 random observations here and 5 random observations there. So you did 5 random things on one system and 5 random things on the second system. There is no relationship between the first observation and the first, second and second, third and third. There is no relationship, right? So that would be unpaired observations. In both cases, you have, in the case of unpaired, you could have different number of observations as well. You could have 10 observations here and 5 observations there. In case of paired observations, you have exactly the same number. Okay? So if you have unpaired observations, then you need a little bit more theory that I haven't taught you. But for paired, we are ready. So we ran two systems, and on the first benchmark we got 5.4 and 19.1. On the second we got 16.6 and 3.5, and so on and so forth. So 1, 2, 3, 4, 5, 6 benchmarks. So the differences are, clearly you just subtract 5.4 minus 19.1, you get minus 13.7. And similarly the difference here, so you get 6 differences. So you do the sample mean, sample variance, sample standard deviation, and since there are only 6 samples, you have to use t distribution. And therefore t distribution, and then you use that t value, and then square s is basically divided by square root of n is 6. So we do that, and the t value for 95 is 2.015. So the 90% confidence interval is minus 7 to plus 7. So our answer is that the systems are not different because it includes the 0. So this is very straightforward. If you have paired observations, all you have to do is they take the difference and then you see the thing. Can I borrow your pen? Do you have another pencil that I can keep?
Yeah.
Okay. All right, so unpaired is little bit complicated. So I don't know whether we need to go through the theory here, but for unpaired you could have different number of observations. And so for the first one, you will have a sample mean based upon the number of observations. For the second one, you will have the sample mean based upon the number of observations. For the first one, you will have a sample standard deviation, and you will have standard deviation for the second one. So you will have 4 numbers so far. All right. In spite of all these big expressions here, this is basically a simple formula for standard deviation, right? All right. After you compute x bar and x bar A and x bar B, you compute the difference and you compute the standard deviation of the mean difference. That has this little bit complication here, because what we are doing is we are subtracting two random samples. And again, if we were to tell you about what happens, and we are assuming here normal distributions. So if you take some numbers which are normally distributed and you take some other numbers which are normally distributed, you subtract them, the variance actually is related by this formula. And some of you who are sophisticated enough can figure it out, that the variance of that difference is this. Standard deviation of the difference is this. And the number of degrees of freedom is even more complicated. But basically, the degree of freedom has this formula. Okay? And so if you can calculate both S and nu, then you can use the T formula as before to compute the confidence interval. All right? However, having said this, while you will do this kind of stuff for this particular chapter, but in future, I will tell you, you don't have to do it. That's why I'm not deriving all of this, because this is the part that you really don't use that much. So I will tell you what you use in a minute. But if you were to do it strictly by the books, as they say, you will have to compute the standard deviation, you will have to compute the degrees of freedom, and then use those in the T value.
Yeah, Dr. Jain?
Yeah.
I was just noticing I have a correction from the errata in the textbook for that equation. It's supposed to be where it says NA for the degrees of freedom, 1 over NA plus 1 should be NA minus 1.
So these should be minus 1 here?
Yeah. Yeah, that's what I have corrected in the textbook.
Yeah, good. So let me write down here.
And then same
13,
thing.
19, slide 19.
Yeah.
NA minus 1. Okay. So please make a correction on this line. NA minus 1, NB minus 1. Now, what he was talking about is errata. How many of you have seen the errata? 1, 2, 3. Okay. All right. So there exists an errata for the book. It's on my website. If you go to my website, click under books, click under this book, then you will find errata, which is 13 pages long. So there are lots of things that have been corrected over the period. Please download that, print it out, and then correct your book, or somehow remember that there is a change. Okay? And so he brought up this issue that we know that this formula, when originally printed in the book, was wrong, and some editions of the book have been corrected. So that's the problem. 13 pages long is from the beginning of the book, but after that we had 20 printings. So each printing is more correct. But so the thing is, some of these might be correct for your particular printing, and some of these might not be. But you should know the existence of the errata. Okay? All right. So this is NA minus 1, NB minus 1. And so we do, and thank you for bringing that up. So now we do this now. So now this is the same data as before, but these 6 numbers are not paired with these 6 numbers. Now we don't know which workload is this and which workload is that. They could be very different. This could be the 5th workload, this could be the 2nd workload, and so on and so forth. So these are unpaired observations. Some 6 random workloads were run on system A, and 6 random workloads were run on system B. So these are unpaired observations. So we do mean standard deviation for the first, and we do mean standard deviation for the second. We do the difference of the mean. We do the standard deviation of the mean difference. This 3.698 came from that big formula. Well, it's not that big. from this formula. Degrees of freedom came from this big formula. So degrees of freedom comes out 11.921. Which is actually not that different. Actually, I could have just used number 12 there because we had 6 observations. But anyway, 11.921. And so 11.921, because that degrees of freedom is not listed in anywhere, so we take it 12 anyway. So we go to the table with 12 degrees of freedom and 0.95, and we find 1.71, and therefore we find the confidence interval for the mean. And now after reading this confidence interval, we notice that the signs are different, and therefore the confidence interval includes 0, and therefore the two systems are not different. All right? Yeah.
So we're comparing two systems and running completely different workflows on them.
Yeah.
So we can actually do that and still compare.
So generally, that example is not a good example, but when you do surveys, you don't ask the same person 2 questions. You ask 5 people here and 5 people there, and then you say, well, okay, so you are for the Democratic Party, what do you think, who will be the nominee? Then if you are the Republican Party, who will be the nominee? These are different people. So these are different workloads. Right? And there is no relationship between this person and that person, right? So that is the kind of thing happens. And so, yes, I mean, obviously you won't be running different benchmarks random and then saying, well, we ran 100 benchmarks here, we don't know what we ran, and we ran 100 benchmarks there. But it could be that you're comparing utilization or something, so you had 100 things run and you calculate the utilization of the today's date, whatever the date is, and then 100 utilization thereafter. So there could be some cases where comparing things which are not related. Okay? Yeah.
Is the value that you get ever misleading? Like, I mean, just because it has a 0 in it, can we infer that there's no difference? Like, you could ask 100 people, what tastes better, beef jerky or ice cream?
Yeah.
If there's a 0, you feel like there's no difference in taste. You know what I mean?
Yeah, no, see, this is why I'm going to bring it up. See, the thing is, okay, so time after time, every day when I watch the news, I do this calculation. When I watch the news, they tell you that Obama won so many percentage and whatever the Romney so many percentage, and so this was like 42 and 48 and 52, right? 4% difference. And then they say that the standard error is 5%. What does that mean? That means they're not different. Right? I haven't defined a standard error, so that, hold on to that thought. But basically, given that standard error, I can calculate the confidence interval. Given the confidence interval, I can say that this is really, they are making fuss about things that they don't know. And the reason they don't know is because they took such a small sample. And that's why the standard error is so large. See what I mean? So yes, if you want to find out if people are interested in ice cream or not, the question is, then you have to make a statement that I could be wrong by so much percentage on this. Right? So given a small sample, you are wrong so much. If you are a larger sample, if they would have taken a sample of the whole United States, then they would have found out that one will win by 1%. 2% or whatever number, right? But they can't do that. So they just make a very small sample and make an observation which has no value, because right there they are saying that I have no data. People don't understand that, but we who are statisticians, we right away say, oh, come on, what are you saying here? So in the very fine print, they put that standard error, which is actually related to confidence interval. So you have to add that and then figure out whether this is the difference is significant. All right. So any other question? So now I'm going to tell you another visual test which is even more powerful, and I find it very powerful. When I say powerful, means I use it all the time. And I don't need to have too much of mathematics done behind it, and that's the kind of thing I want to teach you. So here's the thing. Suppose you have two systems, A and B. Now you're reading a paper. In the paper, they show you the confidence interval, which some people do. They draw two graphs. They put the confidence. So if the confidence interval between the two are such that they don't overlap at all, so the highest of this is below the minimum of that. Our second possibility is that the confidence interval overlaps so much that the mean of one is in the interval of the other. Or they are so different that the confidence interval overlap, but the mean is not in the confidence interval. You get these three cases? All right, so what can we say? Now you could do hypothesis. There are lots of books on statistics that talk about hypothesis testing. So I want to test the hypothesis with the A is different from B, and they give you all the formulas, which we can go ahead and do it. And actually we can use that because these are non-paired observations. We could just use that new formula, get the degrees of freedom, and go to t-value and all that. But we don't need to do that, because all visually when we look at this, I can tell you that basically you can be assured that A is better than B in this case. You can be assured that A is same as B in this case. This is the only case where you need to, you cannot be sure either way. In this case, you need to run that formula. Okay? And why it is powerful? Because when you are looking at the graph, reading a paper, right away you say, oh, they are not different. What they will do is, these guys who have plotted the graph, they don't understand this part. So they will still show you everything, and they will say, look, my curve goes above their curve. My curve is better than their curve. But they don't notice that the confidence intervals are overlapping. Even though the means are not, but the confidence intervals are overlapping so much that the mean of one is in the confidence interval of the other. If that is the case, then means the systems are not different. Okay, so now can you do this visual test? Do you feel comfortable that if I showed you two confidence intervals, then you have to check. What you have to check? You have to check whether they overlap or not. If they don't overlap, decision is done. If they overlap, how much they overlap? If they overlap so much that the mean of one is in the confidence interval of the other, decision is done. If they overlap little, then you need more. Okay? All right. So here is an example. We take the same numbers as we had before. And so we come out with the confidence interval for the mean of A, confidence interval for the mean of B, and now we look at these two numbers. So the lowest here is 0.18 and lowest is 0.24. So the mean of this, mean of B is, where is the mean of B? 5.64 is in here, right? And the mean of A, 5.31 is in here, right? So this is that middle case, that the systems are not different. Okay? All right. Now the next question is, should we use 90% or 95% or 99%? And I have said it so many times that by now you know the answer, right? So the answer is, it depends. Right? Because it depends upon the loss that you will have if you are wrong. How many of you have bought a lottery ticket ever in your life? Anybody? Okay. All right. What was the confidence that you had that you will win it? I mean, chances of your being wrong is what? So suppose 38 million people bought the lottery and you are one of them. Or let's keep it round number. Let's say 100 million people bought the lottery and you are one of them. Chances of winning, without too much work, that 1 in 100 million. So you are going to be wrong I don't know, 9, you put 9,999,999 times, 8 times, that is how much you are wrong. Right? Your right being is you put 7 zeros and then you put a 1, 10 raised to minus 8. That is your probability of being right. So at that confidence, you made a decision, right, and you felt good, is because that you will be 99.999% wrong. So that's why the reason is because the loss is so little. $1 means nothing, right? And the gain is so much. So if you just by chance were right, then you're all done. You don't have to work tomorrow, right? All your life. So the thing is, the gain is so high and the loss is so little that you would rather be wrong than be right. Of course, you want to be right, but you can take chances to be wrong. On the other hand, just change those numbers. You are building a bridge, or building an airliner like 787, and the battery burns up. Have you heard this story? Right? And the battery burns up. How many billions of dollars are you going to lose? The company is going to shut down. How much right do you want to be and how much wrong you want to be? You want to be 9,99999, write down 7 times. That is how much you want to be right. Okay? So even though we are going to teach you all this different 90% all the time, but don't use 90% all the time. It depends upon how much you are going to win and how much you are going to lose, and how much risk you can take. And so for some people, $1 is a lot of value. For them, that lottery ticket is very expensive. For some people, it is nothing, right? And so they might even they might not even buy lottery, but basically I'm just saying that, so that is the thing, okay? So the confidence level, 90% you don't have to have. You could have 0.0001% confidence, and that's good enough in many cases. All right. Now, having said all this, we might just use 90% all the time, but that is just because we are teaching a course. When we go to the real world, we have to be careful about what confidence we use, because if you use 90% for plain design, your company will be out of business pretty soon. On the other hand, if you use 90% for buying a lottery ticket, now here is another example. Suppose you want to be 99% sure. Let's say 90% sure that you build the lottery. How many tickets you have to buy? 100 million people, you have to buy 90 million tickets, right? Would you really gain anything out of that? No, because they don't give you 100 million back. Out of 100 million, they keep 50 million, and they give you 50 million. Right? So for $90 million, you are sure, 90% sure that you will get $50 million. So that's not a good distance. That's the kind of thing is that now, so basically how much you're going to go and lose and how much you're going to win, how much you're going to gain determines how much confidence you want. All right. So the next topic is hypothesis testing versus confidence intervals. So most of the books on statistics kind of emphasize hypothesis testing, and in my view, actually that is little bit too statistical, and we want to keep life simple, and they are same. You get the same answer whether you go this side or that side, and therefore I emphasize confidence intervals throughout from now on. But it is same as doing hypothesis testing. So if somebody did the hypothesis testing, whether what is the probability of whether this is correct and that correct, you will get the same answer. So from now on, basically this is what we are going to do, confidence interval, and they're very powerful because they can be understood by anybody. Actually, people who don't understand confidence, for example, you didn't know probably before today that you could compare the confidence intervals like that, but people understand at least that, okay, this is variance. You can explain to your manager. You can explain it to anybody and they will understand very fast. All right. Now we go to the one-sided. So in some cases, you don't want to take 5% chance on this side and 5% error on the other side. Some cases, the other error on the other side doesn't matter. And the error on one side is the only thing you care about. In that case, you have the confidence intervals, which are called one-sided confidence intervals. So for example, if you want the lower side, then you put all alpha on the lower side. So instead of alpha by 2, you have alpha. So when you want 90% one-sided, you put 0.9, not 0.95. And so you don't divide by 2. And similarly, if you want the upper side, then you put plus, and then you leave it there. And here is another thing too. I might use T all the time, because if you have more than 30 observations, T is same as Z, which means that whether you look at the T table or Z table for 31 observations and 32 observations, the difference is very little. Okay? So T becomes Z when you have more than 30 observations. So if you have a small number of observations, you use this, but if you have more than 30 observations, then that is Z. It's unit normal. All right. So only for small numbers they are different. For larger numbers, the T and G distributions are same. All right. So let's see this. Time between crashes. We had 972 observations. The mean time between crashes was 124, and the standard deviation was 198 on the system B. 153 observations. So here is an example of a workload which is different. So you were asking, can you do different workloads? So here it is the example. So this is the crashes. System A crashes 972 times. System B crashed 153 times, and we want to compare the systems anyway on the reliability case, right? So there is no relationship between these two crashes, and there is no relationship between any of the crashes with any other crashes, right? So we have unpaired observation. All right, so we do X bar and the difference, we do the S, and we do degrees of freedom. And since it is more than 30, we can use Z, and we use the Z, and the confidence interval includes 0, and therefore the systems are not different. The main thing new here is that we used one-sided confidence interval. So we don't have 17.37 minus here and the plus there, because we don't really care if the number is smaller. Okay, so can you think of the cases where you will need one-sided confidence interval? There are many cases where really having something on one side makes no difference. It's not bad. Okay. So if you are doing, let's say, paging in a system, you really want to know whether the paging will be more than this. If you are doing a room, you want to know that the number of people will be more than that. If the number of people is less than something, you don't care. Right? So oftentimes the issues are that if you overflow something, that's bad. But if you underflow, it's not bad. So a lot of times the risk is only one way. So then you use one-sided confidence interval. And you put the error on one side, total error on one side, not half of it. So finally, confidence interval for proportions. So what if it is a fraction that you want to do the confidence interval of? So here is the thing. For example, probability of error is 0.01 and no error is 0.99. And so you do sample. You sampled something and something happened n1 times. So your sample proportion is n1 upon n. So this is your sample. And so the confidence interval for this is whatever is the sample fraction is p minus plus z 1 minus alpha by 2 square root of p times 1 minus p upon n. And so basically, if np is greater than 10, then this is valid. And if it is np is less than 10, then you need to use binomial tables. Again, all of this will require understanding the binomial distribution, and it turns out if np is greater than 10, the binomial becomes like normal. So there is no difference. We can always use binomial. But if it is less than 10, then basically you need to use the real binomial tables. Don't use the t-values. So we are going to, so basically the one-sided confidence interval, one-sided would be either this, which means either plus or minus. So we start from p and go to plus, or start from p minus and go to p, provided np is greater than 10. So here's an example. 10 out of 1,000 pages printed on a laser printer are illegible. So the sample proportion is 10 upon 1,000, which is 0.01. NP, N is 1,000 and P is this, so 10 actually. It turns out it is right on the boundary. It's not more than 10, it's just equal to 10. And therefore we can use this formula and use the z table, and the z value that we will need is for the 90% confidence interval. We are using actually two-sided confidence interval here. So we are going to use 0.95, which was 1.645 z value, and therefore you get this number. 95 percentile, you use 0.975 z value, which is this value. So this is two-sided confidence interval. Now, so the thing is, what this is saying is that this 5 to 155 means that 5%, 0.5% chance to 1.5% chance that the pages are illegible, and you could be 10% wrong in that case, and so on and so forth. Okay, I think that's the end. We will just stop right